Okay, so I was asked to do a short tutorial on error propagation. So let's have a quick look at this. So fundamentally, error propagation is differential calculus. So honestly, if your differential calculus skills are weak, then you're going to struggle with this. Here's the basic idea. So I've got a graph of a function f of x. And f can have any shape. I'm going to draw it kind of parabolic here. And of course, if I take some interval of this particular graph, say here, then that corresponds to some increment in x, and it also corresponds to some increment in f of x. Of course, they're not going to be equal to one another if the graph isn't linear. And so we see that the uncertainty in delta x transforms into some uncertainty of delta f of x. And because you're familiar with differential calculus, you understand that this is related to the slope of the function or its derivative. So I can write the linear relationship between delta f of x and delta x by multiplying by the derivative of the function with respect to x. This is the basic premise of the whole business. So let's have a look at a quick example. So let's imagine that f of x is equal to x squared. Then delta f of x is equal to the derivative of x squared by dx times delta x. That's equal to 2x delta x. Note that I can also divide both sides by f of x, so by x squared, and I get an equivalent solution where it looks like this. And you're going to be seeing this particular term, delta x on x, or delta whatever your dependent variable is, divided by the dependent variable. Because really what it's telling you is that the uncertainty on the function f of x scales as the uncertainty on the independent variable, but multiplied by something that depends on the function itself. So this is an example of a polynomial, right? So x squared. And you can show generally that for any polynomial, so f of x is equal to x to the power of some value n, that delta f of x is equal to n times f of x times delta x over x. Right, and you can carry out this calculation exactly the same way we've done above, and you can show that this is true. Okay, so let's look at an example from the course. So here we're going to take the equation that relates distance and parallax. So distance is equal to 1 divided by parallax. And of course, just as an offhand, I'll remind you that this is d in parsecs and parallax in arc seconds for this particular form of the equation, but it doesn't really matter for the error propagation. So if we think about our general equation that we saw on the previous page, I've got, in this particular case, x is equal to p, and I've got f of x is equal to d, right? So if I write delta f of x is equal to d f of x by dx times delta x, then in this particular context, in fact, what I've got is delta d, sorry, equal sign there, is equal to d by dp times delta p. Okay, so I'm just going to insert the function there. So d is equal to 1 over p. So this is the derivative of p to the minus 1 by dp times delta p, and that's equal to minus p to the minus 2 delta p. So again, if you struggle with understanding how I've computed the derivative of p to the minus 1 here, then you're going to struggle with this whole process. Okay, so in the end, we've got delta d is equal to minus delta p over p squared. But again, I can divide both sides by d, right, by 1 over p. And if I do that, then I get delta d is equal to delta p over p times d. Or maybe a slightly different way of looking at it is that delta d over d is equal to delta p over p. Right? And that should be intuitive to you, because what we have here is a function where there's a direct relationship between one variable and the other. Okay, so that's how it works. And then when you extend this to multivariable functions, all we're doing is adding up contributions from different variables. Okay, so now we've got a function like f of x, y, and z. We need to use partial derivatives because I want to know the particular contribution of the slope in a particular direction. So the x direction, the y direction, the z direction of the function. Okay, so what I'm going to do is define three different delta f's. Delta f in the x direction is equal to df by dx delta x. Delta f in the y direction is equal to df by dy delta y. Let's move this over a little bit. And then delta f in the z direction is equal to df by dz delta z. And then the total uncertainty, right? So the total delta f is going to be the sum of these. And I'm going to sum them in quadrature for a couple of reasons. One, because that's the appropriate way of adding uncertainties, because they're vectors. And when you add up the components of a vector, you add them in quadrature, right? So you add up the squares and take the square root. But also, we want these to be positive, right? And so if we square them, that's going to get rid of any negative signs. And they have to be positive because when you add up uncertainties, you never wind up with something that's smaller than any of the individual uncertainties, right? So delta f squared is equal to delta fx squared plus delta fy squared plus delta fz squared, which is equal to df by dx delta x squared plus df by dy delta y squared plus df by dz delta z squared. And so that's the general equation for combining uncertainties we saw earlier. Okay, so let's look at an example. So let's take f at x, y, z is equal to x squared plus 2xy plus sine of z. Okay, so let's calculate delta fx. Okay, so this is going to be equal to the derivative of the function with respect to x, partial derivative of the function with respect to x, multiplied by delta x. So if I look at the first term, I've got x squared, derivative is 2x. Second term, I've got 2xy, it's partial derivative, so I'm going to treat the 2 and the y as constants. So the derivative of that is 2y. And then there's no x that appears in the last term, so there's nothing there. So delta fx is equal to 2x plus 2y delta x. Delta fy is going to be equal to, well, the first term doesn't have any y, so it's 0. Second term is 2xy. So derivative with respect to y is 2x. So I got 2x here. Last term has nothing relative to y, so that's the whole thing, delta y. You get dogs barking in the background, it's a bonus. Delta fz, finally. Okay, so first two terms don't have any reference to z, so their derivatives, their partial derivatives are both 0. Last one is sine z. Of course, the derivative of sine z is cosine of z. Okay, and then times delta z. So in the end, our delta f is going to be equal to the square root of 2x plus 2y squared delta x squared plus 2x squared delta y squared plus cosine squared z delta z squared, all square rooted. Okay, and it's important to note that this is a function not only of delta x, delta y, and delta z, but it's also a function of x, y, and z, right? So it depends where in the function you're evaluating these derivatives that determines your value of delta f, right? And you can see that, right? If I draw some function, and I don't know, like it looks like this, right? Then at some places, if I've got some delta x here, right, that corresponds to nothing in delta f, right, because the function is flat. Whereas in other places, right, if I take a delta x and it's, I don't know, like here, right, then that corresponds to a very large delta f. Okay, so let's look at an example from the course. Okay, so I'm going to take the Stefan-Boltzmann law, calculated for a spherical star for luminosity. So 4 pi r squared sigma t to the fourth. Okay, so this is the SI version of the equation. So T is in Kelvin, R is in meters, L is in watts. And I'm just going to rearrange it because what we actually do when we're calculating stellar properties, as you know, is we use this equation to calculate the radius with knowledge of the luminosity and the temperature. Right? So I'm going to write this out. So R is equal to 1 over 4 pi sigma to the minus 2 times L to the minus 2 times T squared. Okay? So this is the equation I'm going to be analyzing. So what I want to do is determine delta R, assuming we know delta L and delta T, and the luminosity and temperature of the star as well. Okay, so let's write it out. So delta R squared is equal to dr by dl squared delta L plus dr by dt squared delta T. So that's going to be equal to 1 over 4 pi sigma to the minus 2. Derivative of R with respect to L is minus 2L to the minus 3 squared T squared. right? T acts as a constant. That's all squared, and then plus the second term. Again, we've got 1 over 4 pi sigma to the minus 2. Now I'm differentiating with respect to t, so I've got 2t, and then I've got my constant L to the minus 2 all squared, and here I've got delta t squared, and I've forgotten to put in my delta L squared up here. Delta L squared plus. Okay, so that looks like a pretty complicated equation, but you can simplify by dividing by r squared. And if you do that, then you get delta r over r squared is equal to 2 delta L over L all squared plus 2 delta T over T all squared. And this is, again, just an application of the general rule where you have, x to the power of n. We had L to the minus 2, so we get a factor of 2 out front. And we had T to the 2, so we get a 2 out front. All right, so let's do one final example. So let's take our equation for the distance modulus, 5 log d over 10. And in the course, we want the uncertainty on the absolute magnitude. So we're going to write it like this. So m is equal to apparent magnitude minus 5 log d over 10. Okay. So now applying the error propagation equation, so delta m is equal to dm by d little m squared delta little m squared plus dm by d distance squared delta d squared. So you recall that in this particular case, so if you take the derivative of the equation by little m, right, then you just get the derivative is equal to 1, and so you just get a delta m squared. But delta little m is really tiny, right? So in practice, we just ignore this term. You can include it if you want, it just doesn't contribute anything significant. Okay, so then what we're left with is the derivative of the absolute magnitude with respect to d squared times delta d squared. Okay, so let's remember that the derivative of a log of x by dx base a is equal to 1 over x times ln a. Right, so if a were equal to e, right, Euler's constant, then this would be the natural logarithm, ln x, and you know that the derivative of ln x is 1 over x. And this works because the ln of Euler's constant of e is equal to 1, right? Is e to the power of 1 is equal to e. Okay, so then let's work this out. So that means that, so let's do this. So dm by dd is equal to, so I'm going to take the derivative of 5 log d over 10. So I've got my, that's minus 5, right? Because there's a minus sign out front. So minus 5. Then I've got the log of d over 10. So I'm going to have 1 over d over 10 times the ln of, well, the base of this logarithm is 10. So d over 10 ln 10. But wait, we're not finished yet, right? Because right now we're taking the derivative of a function that's itself a function, right? It's not ln d, it's ln d over 10. So I also need to take the derivative of d over 10 according to the chain rule. Okay, so what I'm actually missing here, need a little bit of space. Right, so now I need to do the derivative of log, sorry, that's not right. The derivative of d over 10 by dd. So ultimately this is giving us minus 5 times 1 over d over 10 times ln 10. And then the derivative of d over 10 is 1/10. So times 1 over 10. Okay, so in the end, if you properly account for all the arithmetic, then this gives you minus 5 over ln 10 delta d over d. And what I've actually calculated here is delta m. Right, so I've inserted this derivative into the equation up top. I will point out that in my course notes, which you'll find at the link in the message, I neglected the first time I went through this to apply the chain rule, so it's wrong in the course notes, but it's corrected in the solution to assignment number 2. Okay, so that's a tutorial on error propagation. I hope that helps.